It was a calm day in Fort Lee, although you wouldn't know it by looking at Maria, a young student of Fort Lee High School, who having just left her calculus class, was absolutely stumped by polar coordinates.
Get it. What's the point of even using polar coordinates? Rectangular system is way easier. Hey! Oh, I can't run in these flip-flops. Somebody help!
What's the matter, man?
Somebody took my bag of magical math performance enhancing dark chocolates. What do I do?
Alright. You need to tell me which way he went and what he looked like.
Okay, he was about this tall. He had a navy blue shirt, khaki shorts. He went that way about 400 feet and then left about 300 feet, but I couldn't catch up to him.
Alright, I'm on. I think this was about 400 feet. And I think she told me to go left. Okay. He's not here. I give up.
Maria begins to realize that maybe her instructions weren't too clear. By the time the officer figured out where he was going, the criminal was long gone, and the officer had wasted a lot of energy running in a rectangular form. Maybe her calculus teacher had a point. Maybe there was more than just rectangular form. She begins to think about how her life would have been different if she had used polar coordinates.
You need to tell me which way he went and what he looked like.
He was about this tall, navy blue shirt, khaki shorts. He went about 300 feet in the 11 o'clock direction.
Alright, I'm on it.
What do we have in here? Oh my god. It's filled with magical math performance enhancing dark chocolate. My god, these things are so hard to come by. It's great. I guess I can take a break. Nice professional thief like me, no one's gonna catch me.
Put your hands up. Put the bag on the floor. Under arrest for theft. You have the right to remain silent. Anything you say can and will be used against you in the court of law.
Thanks to her use of polar coordinates, Maria was able to give Officer Fukura the directions he needed to apprehend the criminal and save the day. As it turns out, polar coordinates, as well as polar functions, can be a great alternative method of representing something that would otherwise be too complex in rectangular or vector form. The more you know!
Let's begin with a brief history of polar coordinates. The concept of polar coordinates dates back to the first millennium BC, with the Greek astronomer and astrologer Hipparchus, creating a table of chord functions giving the length of the chord for each angle in around 190 to 120 BC. It is said that Hipparchus used polar coordinates in establishing stellar positions. Beginning in the 8th century, Islamic astronomers started experimenting with different systems in order to calculate and describe distances, such as the distance from the holy city of Mecca in Saudi Arabia to any place on Earth. In the 9th century, astronomers began to use spherical trigonometry and map projections to measure distances from Mecca. In On Spirals, Archimedes describes the Archimedean spiral, a function whose radius depends on the angle. But it wasn't until the 17th century that Bonaventura Cavalieri employed polar coordinates in order to find the area within an Archimedean spiral, by relating it to that outside a parabola. Gregorio Fontana then coined the phrase polar coordinates. The word polar stems from pole, which originates from the Greek word polos, meaning pivot, axis of a sphere, or sky. The word pole is used later on in the video to refer to the origin of the polar coordinate system, or 0, 0 in rectangular coordinates. Now let's review a couple of pre-calculus concepts. As previously mentioned, the pole is the origin of the polar coordinate system. Additionally, the initial ray is considered the positive x-axis. Each point is identified by the coordinate r, theta, r being the distance from the pole, and theta being the directed angle from the initial ray. And here are the polar coordinate conversion formulas. X equals r cosine theta, y equals r sine theta, r squared is equal to x squared plus y squared, and tan theta is equal to y over x. Formulas in order to convert the polar equation r equals 4 sine theta into rectangular coordinates. So we begin by multiplying both sides by r. Get r squared is equal to 4r sine theta. And we know that r squared is equal to x squared plus y squared. We also know that r sine theta is equal to y. So we can simplify this equation into x squared plus y squared is equal to 4y. And now we have what we need to solve the equation. So we get x squared plus y squared minus 4y is equal to 0. And here we use completing the square in order to solve for x and y on one side. So we get x squared plus y squared minus 4y plus 4, completing the square. And just finishing up, we get x squared plus y minus 2 squared is equal to 4, which is a circle with the radius of 2.
If you wish to review the general graphs of polar equations, please pause the video now. Otherwise, the lesson will continue.
Finally, that we finished all of the basics of polar coordinates, we can finally go on to doing polar slopes. Now, what polar slope is basically the same thing as Cartesian slopes, let's say. So, in Cartesian coordinate system, we had a function f of x, and we had a function itself, and we find the slope of it. Very easy, dx of the function. But in polar coordinates, we have to do dy dx as well. And that is because for polar coordinates, we have a polar function as a function of the radius. Let's say minus 2 cosine theta or something like that. And obviously there's no y or x in it. So what we have to do is convert dy dx somehow from the polar coordinates. In order to do that, utilizing the Leibniz notation, we can do dy d theta over dx d theta. And that is going to be equal to the same thing as d theta of y over d theta of x as a function of theta, obviously. And as you learned in the previous section, y is equal to r sine theta, and x is equal to r cosine theta from conversion factors. And therefore, dy d theta could be also written as, well, dy dx could be also written as d theta of r sine theta over d theta of r cosine of theta. And let's do a quick example of that. One example could be, let's just use this one. R equals 3 minus 2 cosine of theta. And let's find the slope at, let's just find the general slope function. So d theta of r sine theta, which is r, 3 minus 2 cosine theta, sine of theta, divided by d theta, 3 minus 2 cosine theta, sine theta. Oh, my bad, cosine of theta. Right? And from there, it's just simplification and more work in general, but it is 3, well, d theta, 3 sine theta minus 2 cosine theta sine theta divided by d theta, 3 cosine of theta minus 2 cosine square of theta, and take the derivative in terms of the theta, and you'll get 3 cosine theta minus, that is product rule, but it could be simplified as sine of 2 theta, so we could do 2 times cosine of 2 theta divided by 3, what's that, sine of theta, negative, plus 4 sine, 4 cosine of theta times sine of theta. And that there is your function for dy dx in terms of the theta, and you could now solve for the slope at any point with a given theta with the equation. For the equation r equals 3 minus 2 cosine of theta, and this could be simplified more if you want to, but for now it will suffice. Now that we went over polar slopes, we could go on to the new topic, which is polar area. And for this problem, we're going to be using golden chocolates, golden coin chocolates. So let's talk about that. So now that we got the chocolate out, we're going to go over ways to find the area of the particular chocolate. So one of the ways is just using the old-fashioned equation pi r squared. Let's take a paper out. Old-fashioned equation pi r squared, right? That's just the area of a circle. But another way to find out this area is, well, perhaps making little squares like this, graphing paper, and you could approximate that way. But that is not efficient with that efficient, since you can't really know how many squares there are. So what we're going to use are pies. Jesus, tasty. In any case, we're going to use little, small, tiny pies, and we're going to combine a lot of them, right, and make a full circle. Not a perfect drawing, but it will suffice. So let's make markings of chocolate. Now that we made some markings in chocolate, we could measure or estimate what the area of the chocolate is. So there's 8 parts, and one of the sectors can be described in the fashion that 1/2 r squared times theta. That is general equation for sectors or one of the pies, and proof could be accessed online or anywhere else. I don't have much time to do it on the video, so please refer to any other videos online. And the angle here is going to be pi over 4. So there's 8 of 1/2 r squared pi over 4 radians, and the total area is going to be what's this, pi r squared, and that is the same exact equation as up top. And the general idea for this is by combining small ones with different radiuses, with small increments of radiuses, we could make a complete area of a particular object. For example, we could take any shape like a lemniscate. Well, not really, but we could take a shape like this, and we could take sectors out of this as well and make complete areas in the same fashion. So the integral notation for this is going to be our starting point of the angle alpha, the ending point of the angle beta, and the sector area 1/2 r squared. But since the theta is going to be so small, we're going to use d theta, and that is the equation for area for any polar shapes in general. So let's do an example. Okay, so let's try this example. R equals 1 plus cosine of theta, which is a cardioid, as you learn. So first of all, you need to find which direction the curve is going in. It's important. So this curve goes in a counterclockwise direction, straight. It doesn't skip anything. It's always positive. So we could just use this value. So we could just say that the limit from 0 to the top boundary, which could be 2 pi, since it's all positive values, but since it's symmetrical by the x-axis, we could use the identity that 0 to pi times 2 is equal to the whole area. Now we have that. We could do the general equation, 1/2 r squared, which is 1 plus cosine theta squared d theta. Now we could take out the constant 1/2, and that will give us, that's equal to 0 to pi, 1 plus cosine of theta squared d theta, and that's going to be equal to 0 to pi, expanding 1 plus 2 cosine theta plus cosine square of theta times, well, d theta, and that is equal to, well, from simplification and some really complicated, well, not that complicated as you think, but a complicated trigonometric identity, we could have that. That is going to be theta plus 2 sine theta plus theta over 2 plus sine of 2 theta if I divide 4 from 0 to pi, and you could evaluate that 0, 0, 0, 0. If you plug in 0, it's going to be 0. So the whole thing minus 0, since antiderivative of top minus 0, well, bottom, and pi is going to be pi plus 2 sine of pi, which is still 0. Pi over 2, pi, 3 pi over 2, and that's going to be 0. So 3 pi over 2.
So finding the area between polar curves is actually quite similar to finding the area of polar curves on their own, assuming that's the equation for them. So the main difference here is you're finding the area of the polar curve with the outer radius and subtracting the area of the polar curve with the inner radius from that. So the outer radius is denoted by r2 while the inner radius is denoted by r1. So this equation can be combined into the integral from alpha to beta of 1/2 outer radius r2 squared minus the inner radius r1 squared d theta, and that's pretty much it, but this next example will illustrate what I mean by inner radius and outer radius in context. So this example asks us to find the area of between the circle r equals 1 and the cardioid r equals 1 minus cosine theta. So if you'd like to try this on your own, please pause the video now and come back for the explanation. Okay, so the important thing to do here is to draw a diagram, which the textbook does for us, and identify the region that you're looking for the area, which is over there, and find the intersects. So the intersections can be found algebraically by setting the equations equal to each other. So this simplifies to cosine theta equals 0, so theta equals pi over 2 and negative pi over 2. So now you can plug this into the equation from before. So your alpha is negative pi over 2, your beta is pi over 2. We put down our 1/2. The outer radius is 1 squared, that's that outer curve, and the inner radius is 1 minus cosine theta, also squared, d theta. The inner radius is that right there. So now, due to symmetry, we multiply this whole thing by 2, but change our bound to make our lives easier. The 1/2 stays, 1 squared is 1, 1 minus cosine theta becomes 1 minus 2 cosine theta plus cosine squared theta. And then this simplifies again. We can pull the 1/2 out to cancel out the 2. So 0 to pi over 2. The 1's cancel each other out, and you're left with 2 cosine theta minus cosine squared theta d theta. So this is a job for the calculator, so even if you didn't try this on your own, please pause the video now to try this in your calculator. And the answer you should have gotten was 1.215. So if you got that, you clearly have a grasp of this topic. If not, please try revisiting it or ask your local calculus teacher. So the arc length of a polar curve is very similar to the arc length of a parametric curve, which looks something like this. The only difference here is that we are taking our dx dt and converting into dx d theta, and dy dt also goes into dy d theta. So this proof is very doable, however it's long, so I'm going to cut right to the chase. And the equation is the integral of alpha to beta of the square root of r squared plus derivative of r squared d theta. Basically, if you were to substitute the dx d theta and dy d theta for their actual values and combine them, you would end up with these values anyway, which can also be rewritten as integral of alpha to beta of square root of f of theta squared plus derivative of f of theta squared d theta. And that's the basic gist. This next example will help outline its use. So in this example, we are asked to find the arc length of r equals sine theta from 0 to pi. So let's just set up the equation. So our alpha is 0 and our beta is pi. Let's put the square root down, and our r is sine theta, so sine theta squared is just sine theta squared. And then our dr d theta is the derivative of sine, which is cosine, and then that becomes squared as well. And then d theta, so this gets simplified down, 0 to pi. And sine squared theta plus cosine squared theta is 1 d theta. So this simplifies again to the integral of 0 to pi of 1 d theta, which becomes x from 0 to pi, which becomes pi minus 0 equals pi. So now, if you think about it, the graph of r equals sine theta is just a poorly drawn circle in this case, with a radius of 1/2, which means it has a circumference of pi. So this pi matches this pi, so we're all good here.